The PS2 host controller contains a receiver side, as we've seen before. So we will focus now our attention on designing that receiving side, and it's pretty straightforward design. What it does is actually implements this particular timing diagram that we see in here. And it does that using a finite state machine. Before I jump into the details of the finite state machines, you need to remember a couple of things. The receiving system actually is doing only two things. And the first one is actually detecting a negative edge, a negative edge on the clock, and taking some action when that negative edge is detected. And that action is just basically shifting a new bit, shifting a new bit, shifting a new bit. And that's basically what the finite state machine here is doing. So let's dig deeper and see it. So the finite state machine has three different states. So I have an idle state, I have a DPS state, which stands for data, parity, and stop, because it will actually contain the data bits, the parity bit, and the stop bit in here. And the last one is load, which actually loads the FIFO in here. So let's see how this actually works. So in the idle state, first we're going to assert the RX idle, which is here. That tells me that the receiver is idle, and that actually tell it that you can actually transmit. That's why we need it. And then it keeps doing that, and it's like, or actually keeps checking the following question: is RX enable in here? Basically, am I not transmitting? Because you're only enable when you're not transmitting. If you are, and actually the falling edge has been detected, so this finite state machine does not show me the falling edge detector. We'll see it in the code. It's pretty straightforward. But for now, we know that we have a signal, an input signal that tells me if an edge has been detected, a falling edge has been detected. If these two things have been detected, what we do is we have a register we're going to call B, and that register is exactly 11 bits. What it will do is I'll be shifting basically the starting bit, and the starting bit is exactly a 0. So I'm going to shift it. I will be doing basically right shifts and right shifts and right shifts. So the start bit will become the least significant bit eventually. And then we load another register with the number 9, and that's because we have loaded the start bit, which is here. I need to actually load 10 more bits. So from 0 to 9 is 10, and actually we're going to track that. And then after this, we're going to move to the DPS, which is the data, parity, and stop. And in this particular state, all it's doing is actually saying, going in here, checking if the falling edge has been detected. Basically in here, I will basically shift that data bits, and I'll store it in the B. And then I'll check if n is 0. That means I have basically went all the way from 9 to 0. So basically I shifted even the stop bit. If not, I'll just basically keep doing this till I finish. And at the very end, now B will have all of these, including the stop bit and the start bit. And now I can move to the load. And in the load, what happens is I will only take the data bits from D0 all the way to D7 in here. And I'll just basically put them on the RX data in here, or the D out, and I'll issue an RX done in here for one exactly clock cycle, and that basically loads the FIFO. And that's how straightforward it is. So this diagram does not consider, for example, the parity bit or how good the start bit or the stop bit. If you need a little bit more robust design, you need to consider this. What if you received something? You need to check its parity. Maybe you received a bit by mistake or something was flipped. For simplicity, we're just going to focus on the basic functionality of a receiver, which is a falling edge detector, and this particular finite state machine that actually shifts data in, or shifts bits in. So let's take a look at the code to see how this is implemented. So the code is, again, it's pretty straightforward. So we have a few sections. So the section that is called Fsmd, which is the finite state machine with data, it actually just implements this particular diagram exactly as you see it in here. There barely is, or there's no changes, and you can read it. It's pretty straightforward in here. For example, this is the idle, this is the DPS, and this is the last stage, which is load. We're not calling it load, we're just doing it by default. More interestingly, I just want to focus on basically the falling edge detector. And in the falling edge detector, it's a really interesting detector because it's doing a couple of things. So as it turns out that this particular signal here on the clock, it might be noisy, might be glitchy, maybe there's a 1 to 0 or something like that. So in order for us to filter it out, what we will do is we'll design some sort of a filter. So what we'll see is we will define a couple of registers, filter register and filter register next. You can think about it just as a filter, and these are basically the current value and the next value. Okay, so we have a filter signal. So how do we do this? What it's doing is actually reading a clock input, whether it's a 1 or 0, and shifting it into its register. It's basically doing a right shift. So I'm ignoring the least significant bit and I'm pushing a new bit. I'm ignoring the least significant bit and I'm pushing a new bit. So all the time, and it's 8-bit. So what we need to do is we need to figure out basically the filtered PS2 clock. Okay, this is actually the signal that we're going to be using to do a negative edge detector. So it's doing in here, if you take a look at it, it's asking the following: have I seen exactly 8 ones consecutive? And if I have, that means the signal that is coming, which is on the clock, is actually high, which is 1. So if that's the case, I'll just basically make that filtered PS2 clock as high. It's a single bit in here, so if you take a look at these definitions, it's actually just a single bit. You can think about it as a filtered PS2 clock, okay? Now, if I have not seen a bunch of ones, exactly 8 ones, maybe I have seen, I'm going to ask, did you see basically 8 zeros? If that's the case, that means the clock is actually very stable at 0. If these two cases did not happen, just keep the current value of the clock. Okay, for example, you've seen 1, 1, and another 1, and then here, for example, this particular bit happened to be 0. If the current value of that clock is 1, we're just going to keep it. And that's basically it. So what we're doing in here is we're just filtering the clock signal so we avoid any glitches. So if I have a bunch of 1, 1, 1, 1, and then 0 and 1, it's not exactly the clock, it's just a glitch. It'll be just basically, it'll be just out the window in there. Okay, so that's basically just a filtered signal, and then the falling edge is really straightforward. So we have the current value of this filtered one and the next value. If the current value is 1 and the next value is 0, that's what this little knot happens. That means I'm moving from 1 to 0. That means I have a falling edge, and I just assert that. And this is the signal that I will use in the finite state machine everywhere in here. That's basically the falling edge. It is pretty straightforward.